Okay, it looks like it's recording now. Let's make sure the mic's working. Yep, hello, hello, hello. Yep, it is working. Okay, good morning, afternoon, everyone watching this class. I'm going to go over separations lab because I've been getting a lot of comments and concerns about this lab. I've been a lot of comments and concerns because this was your first at-home lab and a lot of you don't know what's going on with it. So let's talk about it real quick and I'll show you how to do it. So first off, in the announcements, you need to use the summary sheets. You're always going to be turning the summary sheets to me. Always, 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 always. If you turn the worksheets in, I'm going to give you a bad grade and tell you to redo it, which you can. Please, 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 the summary sheet. You can find those in the announcements. Next, you need to go back and find the actual lab procedures. This will be found all the way back in week 2, because it was been about a month since we've done this lab. Here's the updated separations lab. Now, if it's your first time looking on it, that's not good. If you've done this lab before, that's great. You can just copy your notes over with. If you haven't, I'll show what's going on with this lab and what to do. So what you're going to do is you're going to click on this link first off. It's going to bring you to this thing right here. Now, if we go back to the updated procedures, step by step tells you what to do. First, it says select solvent 1 and to make that 100% hexane and 0% ethyl acetate. Solvent 2. And then you keep on rating it, shows it take pictures, which you can take screenshots of those experiments or just draw it out. I don't care either way. And then it repeats it by basically changing the amount of stuff every time. So I'll show you how to do that. So here is the experiment. So first off, we're going to move the thing all the way up to this and this. Can't make that thing go away. That was kind of annoying. So let's talk about what's going on. So we have 2 chambers here. Inside these chambers, basically, I have some solvent, which is a liquid. So the solvent is either going to be polar or nonpolar. The more hexane you have, the more nonpolar it is. The more ethyl acetate you have, the more polar it is. And you can see that by this bar right here. What's going to happen is through diffusion, the ethyl acetate or hexane or whatever the mixture it is will move up this plate and go all the way to the dotted line. Normally, you want to stop at the dotted line. Talk about why in a little bit if we don't. So let's talk about this plate right here. This is called TLC plate. So if you're asked to tell me what a TLC plate is, please do not tell me it's a tender loving care plate. It is not. A TLC plate is a thin layer chromatography. Let's break that word down. Thin layer means there's little tiny layers between the things. So these little hexagon things are silica. And the little tiny lines in which the fluid will go through and stuff inside these little polar molecules will bump into and try to go through. So that's the thin layer part. Chromatography is telling us what is inside of something. So right now I have a mixture of polar and nonpolar molecules. Blue would be nonpolar, red would be polar. Silica, little tiny hexagons, is a highly polar substance. So the polar molecules adhere to it really well. And the only way to get them to move is if my solvent is more polar than the silica to move them. That's why down here it says the silica is a stationary phase because it keeps things stationary while the liquid will move up. And as you'll see, what happens is with 100% hexane, the polar molecules will not move up. With 100% ethyl acetate, they will move up. And you can see that as soon as I hit the start experiment button. Yeah, as you can see, as this is going up, like I told you, 100% hexane will not make the things move. However, 100% ethyl acetate will. So this is a bad example because these should be separated because they have different type of molecules. Polar and non-polar molecules are different. So it's going to basically say blah, 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 right? If non-polar solvent is used, nothing happens. RF value is 0 in this. So now let's talk about what an RF value is. An RF value stands for retention factor. And what that means is how much this stuff sticks inside the silica. Well, what we can do is we can assume this is a distance of something. You can measure with a ruler or you can assume it's a distance of 1. So assume it's a distance of 1 centimeter. because it makes the numbers really, really easy. So it's 1 centimeter. What happened is in the solvent 1 with 100% hexane, nothing moved, which means they were retained 100%. So nothing moved. The RF value, is equal to the total thing, the entire thing, which is 1, over the distance traveled, which is 0. So 0 divided by 1 is 1. So the RF factor is 0 because nothing moved. And this one right here, we have 1 over 1 because the bottom number is the distance, the entire distance of the thing, which is 1 centimeter. The top number is the distance traveled, which is they traveled the entire thing. So 1 divided by 1 is 1. So the RF factor for the first experiment will be 1. So what you're going to do is write that in your lab notebook, but also go to your summary sheet, which is summary sheet right here. Solution 1, solution 2. Solution 1 was 100% hexane and 0% acyl acetate. This was 0% this and 100% that. So the RF values would be, 0, 0, because they didn't travel. This would be 1, 1. This entire distance right here is 1 centimeter. 1 centimeter. Technically, all this will be 1 centimeter because we're basically using the exact same TLC plates. We're not changing anything at all. So how far did the lowest priority molecules move? The blue molecules. They moved 0 centimeters. These guys also moved 0 centimeters. These guys moved 1 centimeter. These guys 1 centimeter. There you go. In solutions 3 and 4, we're going to change it up a little bit. This will be 75%. This will be 25%. This will be 25%. 25%. This would be 75%. 75%. So you need to run the experiment again using new values, and I'll show you how to do that. But I will not calculate the RF for you. That is something you have to do on your own. A little bit of work you have to do. So you should see more separation going on now. Not as much, but you will, and you do. In chamber 2, you already see that the molecules are being separated, which is what we want. It tells us there's different components in it, which is good. So you gotta wait for the entire experiment to run. It is a good thing this isn't a done in-class lab. It does take forever, and TLC plates are notoriously hard to do. So it is a good thing we're doing this lab online. Okay. As you can see, it tells you blah, blah, blah here. But what you can do is to find the RF value. Remember, this entire thing from here to here is 1 centimeter. Here to here is 1 centimeter. So you can either roll this out or eyeball it. How far did this guy move? How many centimeters? How far did this guy move? How many centimeters? Same thing, same thing. You then will take that information and add it in here. The last trial, you'll do 50%, 50%, and you'll figure out what moves. You have to fill the rest in. I will not do that for you. You will. If you have questions, you can always email me. That's part of part A. Now, this is the part that confuses a lot of you. Same thing, we'll pick the solutions basically. 1, 2, 3, 4, and 5. So solution 1 was 100% hexane, 0% ethyl acetate. This was 0% this, 100% this. Right? We're going to keep it going. Boom, boom, boom. Just keep on going straight on over. If you don't know what I'm doing, I'm just following the instructions. Right? Okay. Next up, this would be solvent 3, which is 75, 25. This would be 25, 75. This would be 50, 50. So now we want to rank the polarity of things. And the things we're ranking the polarity of are the solvent, the polar molecule, less polar molecule, and the silica gel. So in this thing, which was the most non-polar? And the first one would be example of the solvent. The reason the solvent is here because it's 100% hexane. Hexane is non-polar whatsoever, right? And if you go look, the RF value the bipolar molecule didn't move at all, right? So the highest polar thing was the silica. Next would be the polar molecule. And then it would be the nonpolar molecule. Nonpolar or less polar molecule. Cool. Over here, both things moved. So the highest polarity thing was the solvent in this case because it was 100% ethyl acetate, right? And then it would be a little bit of the silica gel. And then it would be the polar molecule. And it would be the nonpolar molecule. Because, right? And the rest you can kind of do in your, I cannot spell. There. The rest is kind of on your own, right? But the more ethyl acetate you have, the more polar things are. And hint, hint, wink, wink, around these last two, the solvent and silica are almost the same strength. But I would recommend putting the solvent here. Hint, hint, wink, wink. And then the silica. And then you can figure out the rest on yourself. That's what I'm looking for right there. Right here, you got to tell me which solvent or which solution number was the most and least polar. Well, I'll do the first two for you. The least polar was solution 1. The most polar was solution 2. It was because solution 1 only had 100% hexane. Hexane is non-polar whatsoever. Thus, it's the least polar. So 100%, 0. This was 0, 100%. The more ethyl acetate you have, the more polar you are. The more hexane you have, the more non-polar you are. Fill this chart out the way you do. Here, you can put some answers. So how does the distance of the more polar molecule vary with increasing solvent? Just look at this chart and tell me if increasing the amount of polar solvent, ethyl acetate, how does that affect the RF value for the high polarity molecule? Down here, E is asking for how does increasing polarity affect the low polarity molecule? If you put it doesn't, that is wrong. It does. Think about the reaction between oil and water. The more polar you have, the more it's going to move something up, right? Okay, that's what that is. So part B is where it gets a little confusing. What part B wants you to do is look at these chemical compounds right here. Aspirin, caffeine, acetaminophen, and ibuprofen. The structures don't really matter. You don't need to know about the structures at all. Melting points do not care. For this lab, I only care about these guys right here, the solubility in water. Now, you guys should know this, but if you don't, water is a very polar molecule, right? Water and oil don't mix, but water can get rid of most polar molecules. So when it's asking the solubility in water, it's asking the solubility in a polar substance. So you want to do is you want to make all these guys the exact same units. The units I did for my examples were grams per milliliter. That's the easiest way I found in grams per milliliter. You're going to have to convert these guys to do that. If you need help with that, let me know. But I'll let you know this is that in centimeters cubed, 1 centimeter cubed is equal to the same thing as 1 milliliter. Here, with acetaminophen, what's really weird is that, hey, I give you grams over grams. What that mean? Well, 1 milliliter of water is equal to 1 gram. That's the density of water. So knowing that, you can use the density of water at 20 degrees Celsius to change the kilograms to grams and then change that straight over to milliliters. That's what you would do. Once you have that, you're going to look at the TLC plate. Here. And you got to figure out which one is this. So the solution being used for this guy is 100% ethyl acetate, which is 100% polar. So the higher solubility in the water, the more it should move up. So this is the most polar. This is the second most polar, third, and fourth. Tell me what it is, like caffeine, acetaminophen, aspirin, ibuprofen. The solvent front, you give us any number. I measured out my ruler, it was 4 centimeters, but if you want to make it 1 centimeter, go ahead. Spot distance. Spot distance, you're just going to put 0 because that's the line right there. The first line is 0. Then the RF factor is how far the dot moved up over the total distance of the plate. So that guy right there probably moved about halfway, so probably like 2 centimeters. Probably has an RF of 2. This guy probably like 10%, so probably an RF of 0.1. Say 25%, so an RF of 1/4 or 0.25. Right? Oh, so that'd be RF. So that'd be 2 centimeters over 4 would not be 2 RF. It would be 1/2. Sorry, 0.5. Usually in decimal places. Here, I would say it gets a bit higher, probably 75, so 0.75. There we go. Stuff like that. That's what you would put there. I apologize. Let me put it back up so you guys can take a bit quick of that real quick. Whoops. There we go. Okay, you can pause the video now. Now I'm going to delete it so you guys have more time with it. Okay. And here, what's going on is that I theoretically ground the powder up of each of the compounds and put it here. For using this information, you can figure out which dot is which compound based off of this. So the one at 50%, this one is going to be the same one for this one as the same one as up here. That dot right there, same dot as there. That dot right there, same dot as there. Boom, that's what you can do. It's the exact same RF values. The difference is the composition and compounds involved. That's what I care about for that one. Now, post-lab questions you can answer by reading the lab manual, but it's going to ask for streaking. Streaking occurs mainly when a dotted line or the spot line or spot distance is overflooded with stuff. You usually get a pipette and you put a little tiny dot. If you put too much of it, too much stuff sinks in and it kind of drags itself along the TLC plate and it leaves a big kind of splotchy thing. It kind of would look like, if this was a red dot right here, it would kind of look like this, and that's bad. Because what happens is there could be another compound in the same dot, in the same streak that I wouldn't know about. So that's what happens. So what steps you do? One, redo your TLC plate. Make sure you do not have enough. Make sure you have a little bit, not too much stuff on the dotted line or spot line. And lastly, what I would recommend is using a UV light to check to make sure the thing is soaked through enough, but not too much. So number 2 is asking, why is it essential to mark the stuff on the dotted line and not below it? Well, the reason is because, remember, we placed this thing inside of a container full of solvent. If that thing is, if the polar molecules touch the polar solvent too quickly, and don't adhere to the silica gel too soon, they get pulled into the solvent and they won't run on the TLC plate. And there's no point in doing the TLC plate if there's nothing on the TLC plate. So it will dissolve or break down the stuff. What was the main factor that caused it? That most likely that would be the polarity of water, or the polarity of the molecule. The polarity of the molecules would be the best one to answer that one. That's where I'd recommend showing the work for the medicines, because I do need to see the work to make sure you guys did it. And then what role did the difference of the structure of isocyl acetate and silica play in this? What that basically means is ethyl acetate was polar and silica was polar. Well, the difference it is ethyl acetate is way more polar than silica, which allowed it to move the polar molecules out of the silica when they adhered to it during the stationary phase. Good. Do not attach the images. I checked that in class. Do not do that part of it. But that is how you do this assignment. Hopefully that clears some things up. The assignment is due Sunday. If you need help, please reach out and email me. I'll try to email you as best as I can. My email has been down recently, so I have not been answering emails. do apologize, but for some reason, I have 2 email accounts and they switch on and off between each other, depending on, I guess, every time I hire a new IT person, they turn one of my emails off and they turn it back on. It's very annoying. I do not understand why. I've contacted the school today because it wasn't a holiday today, and it looks like my email is back up and running. So I do apologize. I've been lacking on answering emails. That's why. Okay, there's the video. If you have any questions, please email me. Thank you. Have a good day.